In today's lecture, we're going to be building upon our rudimentary freq-C modeling skills by exploring some more options for setting up carbonate equilibria simulations. This is continuing with our simple example from the last lecture. Then we'll move on from equilibrium phases for a fixed mineral composition to a variable composition solid solution. And finally, we'll look into equilibrating a solution with a gas mixture. So let's just start out with a reminder of what we were doing in the last lecture and what is really the simplest definition from last time. And that's just specifying component concentrations at the beginning of a simulation without any other constraints. So for this very simple model, we've just specified initial concentrations of calcium and inorganic carbon and nothing else, and run the model and got a resultant calcite log saturation index as output, for example. Alternatively, we can leave the starting water elemental composition blank, or basically setting it as deionized water, and then adding an equilibrium phase. Note that not all the calcite dissolves here, and because the starting water composition is unbuffered, that relatively small amount of calcite dissolution leads to an appreciably elevated pH value. But there's yet another approach for setting up a problem with the same constituents. Here, we set the calcium concentration to be in equilibrium with calcite at the specified pH and inorganic carbon concentrations. This is done with the mineral name listed after the concentration in the input file, followed by the log saturation index. So let freq-C calculate the inorganic carbon concentration via forced charge balance, adding or subtracting as needed. Note that these two steps, 1 and 2, need to be solved simultaneously. freq-C will take care of this on its own. I'm mentioning this approach because this kind of thing is very useful for setting up initial conditions for more complex models. In the output, note that freq-C has done everything we've asked and has maintained a constant pH. So while we're on the subject of carbonate equilibria, let's look at a couple of new keyword blocks to wrap this part up. These include reaction temperature. Here we're changing the temperature of the simulation from 10 degrees C up to 25 C over 15 equal-sized steps. And we're using selected output, another keyword block, which directs model output per step to an external text file, which we can use for plotting and other sorts of analyses. As to the results themselves, note that the log saturation index of calcium in this system, as defined, increases with temperature. So a separate calcium carbonate mineral phase would not exist in cool water with these values, but would be stable in warmer water. This is something to think about when you ponder the existence of coral reefs. Okay, let's now step up in terms of model complexity and start looking at additional freq-C capabilities and keyword blocks. First, we're going to consider solid solutions, or variable composition solids that respond dynamically to changes with the equilibrating solution. With solid solutions, the effective equilibrium constant of a variable composition mineral is weighted by the mole fractions of the pure end member phase equilibrium constants in the solid solution stoichiometric mixture. This is basically an extension of Rayle's law. Our second example, similarly related to the concept of a mixture, will entail a multi-component gas phase. Our solid solution example concerns anchorite, which is an iron manganese containing dolomite. The ternary diagram shown on the left provides some insight into possible compositional variations that may exist among different carbonate minerals. In reality, which solid solutions form is a complex issue that involves structural details of the crystalline minerals, including the sizes of the different ions. Anchorite does exist, and it possesses a dolomite structure with substituted iron and/or manganese. It's also worth noting that the precipitation kinetics of dolomite can be slow, so while this model shows how an anchorite composition may occur, the rate at which such a reaction could take place in a groundwater system responding to a perturbation from equilibrium is unclear. Defining an ideal solid solution in freak C is easy. Just invoke the solid solution's keyword and list the component end member phases along with the starting number of moles of each phase present at the beginning of the simulation. Non-ideal solid solution models can also be constructed with the solid solutions keyword block, but these are complex and require data sets that are often not available or applicable. So in this example, we'll be adding organic carbon as a reactant to a system that is initially in equilibrium with the solid solution, which is essentially starting out as a pure dolomite, plus iron and manganese oxides and CO2 gas. As the organic carbon is added and reacted, the system will become more and more chemically reducing, resulting in the dissolution of the iron and manganese oxides. Where will the iron and the manganese go? Well, the simulation results show that an ending anchorite composition containing about 6% iron and 1% manganese is formed. Remember, if you look back at the setup input file on the previous slide, you'll see that we started with a pure dolomite that contained no iron and no manganese. Interestingly, the saturation indices of pure iron carbonate, otherwise known as siderite, and pure manganese carbonate, which is referred to as rhodochrosite, remain well below zero, and you can see this on the graph on the right. This indicates that the pure phases for these two minerals would not precipitate in the solution at the same time. Thus, this sort of simple demonstration shows that co-precipitation is an important control on the solubilities of some elements in certain situations. So turning to gas mixtures now, we're going to start by specifying a typical starting groundwater composition, and then again adding some organic carbon as a reactant to bring about chemically reducing conditions, just like we did in the last problem we just discussed. Gas phases are defined under a gas phase keyword block and can be defined as either fixed pressure or fixed volume. The identities and starting partial pressures of the pertinent gases are defined as shown here, and the system is allowed to evolve with the constituents exchanging between the aqueous and the gas phases until equilibrium is reached. Note that for a fixed pressure gas phase, no gas phase will exist until the combined partial pressures of each of the component members exceeds the specified pressure constraint, in this case a value of 1 atmosphere of pressure. So this is what the output looks like with respect to the gas phase. Freak C summarizes the resultant total pressure and volume, as well as the partial pressures and the moles associated with each of the gas constituents in these tables that are present in its output file. For this example, the chemically reducing conditions yield a mixture of methane, carbon dioxide, and a small amount of hydrogen sulfide under the assumption of chemical equilibrium. So for this module, here are a couple of questions for you to consider. How would you set up a simulation to track pH and calcite saturation as a function of pressure as opposed to a function of temperature like we did in the exercise in this module? And then separately, what hydrogeologic settings might justify the assumption of a fixed volume gas phase versus a fixed pressure gas phase?